In this installment, we're going to introduce a new concept. The idea is impulse, and it's very much related to thinking about things as a system. To define impulse, we will say that impulse is the amount of momentum transferred from one body to another in a system. Now, what I find funny about this when you look up definition of impulse, the definition you will find is not what I just gave you. Impulse is the amount of momentum transferred from one body to another in a system. But when you look it up, you'll find it's the product of the average force and the time it's applied. So in other words, impulse J is the average force multiplied by the time it's applied. Now the name impulse comes from the Latin impulsus, which means pressure, and it's related to the Latin pellere, which means to push. Pellere, which means to push. Pressure, push. So, if we have one body transferring a momentum to another body, for that to happen, you see it's going to push on something. That push or pushes are things we call forces. If we push on something, we apply a force. That's just in regular common language. We push on something, it's a force. So there's some kind of average force, and the longer we do it, the greater the momentum will change. You could think about this, when you're riding your bicycles with brothers, sisters, neighborhood, and so forth, right? You got your bicycle, and you're on the bicycle, and someone's going to push you. If they push you and run alongside you for 1 second, your speed is going to go up. You're going to have a change in velocity. But if they do it for 3 seconds, you're going to end up going even faster because they're applying a force for a greater length of time. And it might stand to reason that if they applied it for 3 times the length of time, you go 3 times as fast. So that's sort of the idea behind impulse. All right, so let's talk a little bit about the units. So the definition of impulse, it's the amount of momentum. Well, if it is the amount of momentum, it must have the same units as momentum. So it must be kilogram meters per second. You see, it's the amount of momentum transferred. All right, so it has the same units. The units of force are newtons, capital N, and the time is seconds. So what we will observe right off the bat is that a newton second is equal to a kilogram meter per second. They are the same units. But even though they are equal to each other, this is the unit we think of for momentum, kilogram meters per second, and this is the unit we think of for impulse. Even though they're equal to each other, if we're talking about impulse, we use newton seconds. If we're talking about momentum, we use kilogram meters per second. It's not wrong to mix them up, but we're not quite conveying the true spirit of what's going on. Well, if impulse is the amount of momentum and momentum is a vector, then impulse is a vector. Now let's see, if I have an object moving along and it has some momentum, P, and I come along and I push on it and give it an impulse, this cart afterward is going to have the momentum it had P0 plus more momentum. Plus some new amount of momentum we will call the change in momentum. So the impulse is equal to the force times the change, average force times the change in time. And we know the change in momentum is m delta v. Well, if the impulse is the amount of momentum transferred and it's the change in momentum, then these two are equal to each other. I call this the four-way equivalence. By definition, the impulse is the average force multiplied by the time. That is the amount of momentum transferred from one body to another in a system. So that impulse brings about a change in momentum, which is mass times velocity, yielding this four-way equivalence. So, impulse imparted. Let's do a little example here. We have a car coasting on a horizontal track. 1.0 kilogram, and it has a velocity of 4.00 meters per second. All right, and so then an observer gives it a push, and now afterward, it has a velocity of 5.00 meters per second. Let's see, law of conservation of mass. The masses are the same. So we have this initial momentum, which is mv, which is 1 times 4, which is 4 kilogram meters per second. And afterward, we have a new momentum, 1 kilogram, 5.004, 5 kilogram meters per second. Now we know delta P is P minus P0. And our final was 5, and our initial was 4. So the change in momentum is 1. Well, the change in momentum, 1 kilogram meters per second. So that's our change in momentum. What impulse did it receive? Well, the impulse given is equal to the change in momentum received. So the impulse given must be 1 kilogram meter per second. The impulse it received was also 1 kilogram meters per second. If the time, what is the rate of change in momentum? Delta P over delta T. The change in momentum was 1 kilogram meters per second. And that was 0.10. So the rate of change of momentum was 10 kilogram meter per second squared. Wait a minute. The rate of change of momentum was 10 kilogram meters per second squared. Now let's find out the force. J equals F bar delta T. The impulse, well, we want the average force, so that's going to be J over delta T, and the impulse was 1 and over 110, which is 10 newtons. Wait a minute. They're the same. They are the same. The definition of force is the rate of change in momentum. The definition of force is the rate of change in momentum. Well, let's do a little bit more here. Let's see. Force is delta P over delta T. And delta P is m delta V over delta T, which is ma. F equals ma. This, my friends, is what is known as Newton's second law. F equals ma. But it's really m delta V over delta T, which is really delta P over delta T. The definition of force is the rate of change of momentum. If we follow it through to its logical conclusion, we end up with F equals ma, which is Newton's second law. So the force applied was 10 newtons, or 10 kilogram meters per second squared. Now, going back up to our units here, we said kilogram meters per second is Newton seconds. Let's solve for newtons. Well, to solve for newtons, we would divide both sides. Let me just put this over here. Newton seconds is kilogram meters per second. And to solve for newtons, we get newtons equals kilogram meters per second squared, which is mass times acceleration. The units all work. And that's the definition of force.